Hi. So last week we talked about lists, and lists are sort of an you can say containers or data objects in R that can hold different data types. So they can have integers, they can have vector, they can have like variables, they could have vectors, they could have data frames, they could have list inside a list. So it's like an sort of a data object which can hold multiple data types and would be quite convenient to hold the data hold values during the course of our analysis. As and when we are creating new objects, we can keep on storing there, and that can provide really a good storage point of all those data sets. Then we moved and talked about matrices, and matrices are, you can say that two-dimensional objects which has a single kind of data type inside them. They don't allow mixed type as in the case of lists or as in the case of data frames. So the data frames can have a column, one column can be characters, another column can be integers, then doubles, and so on and so forth. Matrices are not like that. They need to have everything of exactly that. The data is homogeneous. All the data types are of single type. And we looked at some of the examples of like how we are going to create matrices, and we look at some of the operations of the matrices as well. So let's say some of the matrices we look at MRC. Yeah. So for example, one of the metrics is MRC. Then we had MRC3. So these are two different kind of matrices, but pretty much the dimensions are the same. So this has 5 by 5, so 5 rows and 5 columns, and the same is over here. We look at some of the addition properties, which is like element to element additions. The first element of the element in the first row in the first column, or the element 1, 1 is added to the element 1, 1 for the other matrices. So this is like value to value additions. And similarly, when we look at a simple multiplication, the simple multiplication was again from value to value multiplications, like 1 is multiplied by 1, 6 is multiplied by 2, and we get 12, and so on and so forth. Finally, towards when I was concluding the session, I just showed you one of the other kind of, which is generally referred in algebra, linear algebra, as dot products. So dot product of two matrices. And this looks really very different from the rest, what we have seen before. It doesn't look like it's an element to element kind of multiplication. So it's a little bit more complex. And the question is like, why do we need any kind of dot products? And how can it be really useful? So towards that, just to explain the dot product part, and I'm just going to introduce to you like an example, and then we will look how it can help in a real life scenarios. So I'm just going to construct a matrix here, and the matrix is called customer. So let's have a look at the customer matrix. All right. This example is not there in the material I have signed. This is I just created today itself. So here, what it is like, we have information about 3 different customers or individuals and their preference for an eat out place, and what do they look for when they try to go or choose an eat out place or a restaurant to go to. So the scoring is in the scale of 1 to 5, 5 being really looking for really that's the crucial thing to decide, and 1 they don't really care, or basically if it is okay if they have or not have that particular property or attribute. So for example, Liz, she's particularly very particular about the ambience. So she really like to go for good ambience, and food could be a decent quality. If she has to wait to get a table, she is fine. If your parking space is available, she's not really fussy about that. Then we look at Adam. Adam is not really too much in ambience, but he's more particular about the kind of food a restaurant provides. And he's not really keen on waiting and looking for parking for a longer period of time. And he would like to have a convenience of parking his own vehicle. Now, when we look at Jill on the other side, Jill has like really high preference for ambience, very good, like to have very good quality food, and no waiting and no parking waiting as well. So these are, you can see these are the 3 individuals looking for certain kind of characteristics when they choose a particular restaurant. Now, let's say there are 5 restaurants around that place we are living, and we're trying to provide, we're going to put a recommendation for them, okay, which one would suit them the best. So how do we go? So let's look at some of the attributes of the restaurants first. So that's where I created another matrix called REST matrix. And if you look at the restaurant or the REST matrix or the restaurant matrix, these are 5 different restaurants we are talking about. So this is Chili's, Buffalo Wings, McDonald's, Burger King, and Dogland Cafe. And each of these restaurants has, you can say, the same attributes what these individuals are looking for. So each restaurant has an attribute like ambience, which basically really high ambience if the value is 5. And if not that great, then it goes towards the lower side. And so food, waiting, and parking for each one of those ones. Now, for each, if you look between the 2 matrices, what is we are looking at is Liz is choosing a restaurant based on these 5 properties. And these are 5 restaurants with basically 4 properties. And these are the 5 restaurants will have these 4 different attributes. So how do we go about recommending it? So basically, we can't recommend, it's very difficult to have 5 values compare, like take these 5 value choices by Liz and look for all those 5 and compare across the restaurant, because they're not exactly the same. So there is no, you can say, comparing all the elements is not really straightforward to recommend a particular restaurant. So what's the alternative way? If somehow we can provide for Liz a score for each restaurant, a single value that can help her basically the single value help us decide that, okay, which one is she preferably would like to go for and which she is not going to go for. So that's where the dot matrix comes into picture. What it does, it basically takes the 2 metrics and present a single value for each of these attributes. So I'm going to explain it in a while, but what essentially happening is, if you this is where we did the dot product of both of them, and this is what we have got. So these are the values for Liz for each of these different restaurants. How these are generally attained, and so let me have a okay, right. So I'm going to take a paper and sheet, and maybe that will be much better. So let's say Liz has, so we're going to take first the Liz, and she had preference for ambience, food, waiting time, and parking. Her choices are, let's say these may not be matching in the data frame there, so I'm just putting some random values: 2, 4, 3, 1 again. Okay, now let's rather than comparing all the 5 restaurants, for convenience sake, we are only going to look into 2 of those ones. So let's look at 2 restaurants, and we'll try to first compare which one she would go for if we provide a choice of Chili's versus McDonald's. Okay, and in 2 restaurants, then we have again ambience, we have food, we have waiting time, and we have parking. Okay, and then again, I'm putting some random values here. They may not match to what is there, but okay, essentially 1, 2, and here they have 1, 3, 4, and 1. Okay, so now what we have is Liz. These are the preferences of Liz for those 4 attributes, and these are 2 restaurants having these attributes, and these are the scores for those ones. So in order to get a single value, what we do is we multiply each of the attributes from Liz to the corresponding attribute in the restaurant. So what we're trying to do is for Chili's, the Liz, what the score would be. So we multiply ambience by the ambience score, so 2 times 4. Then we sum it up with the next score, which is like food versus, which is 4,4 in the Liz choice, and 4 is for the restaurant, 4,4. Then we add up 3, do 3,1 in the same way, because we are comparing the waiting time of choice, preference of Liz for waiting time and the waiting time for a given restaurant. And finally, we look for the parking, and 1 versus 2. So 1 multiplied by 2, and we put basically do the multiplication and sum it up. So this is going to be 8 plus 16. This is going to 24 plus 3, 27. 27 plus 2 is 29. That's the score we got. So Liz has a score for Chili's and MACD So this is 29 over here. So let's do the same thing for her choice. If she would like to go for the MACD, what her score would be. Or basically, if we compare her choices versus the MACD, what offers, what the score would be. So we're going to multiply 2,1, which is the 2 of ambience versus ambient score of MACD. Same, Then we're going to multiply 4 with 3, 4,3 plus then 3 multiplied by 4, and finally 1 multiplied by 1. Okay, so this is 2. 2 plus 12. So this is 12 and 12, 24, 24 and 2, 26 and 27. So if you look here, I mean, so what we have done essentially using, this is only one individual, but for her, for each restaurant, we were able to calculate a score like 29 and 27. So based on this, we can definitely recommend that Liz would be more likely to go for Chili's. So we can make recommendations for her. And similar kind of recommendations generally work if you have a subscription for like Netflix. So each year, when you start watching movies or start watching programs on Netflix, at the back end, they start calculating a bit, start collecting data like, would you like more humor? Would you like more drama, horror? And they put some sort of a weightage for each one of those different kind of movies. And then we have different movies, thousands of different movies. In each movie has certain marking, what component of it is, of that particular movie is like humor versus horror versus drama. And then they calculate a pretty much similar kind of a matrix, and they develop the scores. Based on those scores, then they end up coming and putting your recommendations that, okay, this might be the movies you would be liking. Now, this is you can say real life scenario kind of where you can do dot products of this one. In case of bioinformatics, we'll see one example where we do is when we try to normalize our data, we pretty much take an account, pretty much use a similar kind of matrix multiplication, or do dot products. Okay. Any questions with respect to that? Hopefully that makes sense. What we did, that we basically decomposed the two matrices into two single values to it, so that now we can evaluate the we can evaluate the choice between two different restaurants over here.
Actually, you have the AFWP on the top as column headers. Yeah. Right. And then their rows going the other way.
Yes. So that's what generally you would like to have that. That's what the critical part of the basically a matrix multiplication is. That's how the data are stored.
Do they have essentially? They've got to be in the same row. They got to be in the same order and everything too, right?
Yes.
You can't have a different order.
Yes, that's true. Sorry. Sorry, I muted you, so you can unmute yourself. I'm sorry about that. But essentially, what is essential in all of this one is this, that the number of rows, the number of columns we have here have the same number of columns should be, same number of rows should be here. So that's the really primary criteria for a matrix multiplication. Essentially, if we have a matrix, so that's if you have a, if we have two matrices, and let's say matrix A, and we're trying to do a dot product with matrix B, if the dimensions of the first matrix is m, comma, n, the second matrix has to have n, comma, p. So basically, the number of columns in matrix 1 has to match with the number of rows in the second matrix, or the matrix B. Now, what it allows us, so because m can be any number, so we can look for as many different, here in case of our customer one, this was the customer. So we can have as many different customers, even if it goes to 100,000, that's not a problem. But here the attributes are 4. These are the 4 attributes, and these are the restaurants again. P represents the restaurants. And this again can go from hundreds to millions, whatever the value. We don't really care. It could be any number, as long as these inner attributes, which is like the column of first matrix and the row of the second matrix, are the same. You can do the multiplication, and you will get a single value decomposition of for all those parameters. So for all the 100,000 customers, we can get the preference across like whatever either 100 restaurants or millions of restaurants, we can make recommendations. If they move from city to city, we can say, okay, in which city, which restaurant they would like to go to. And the same is applied pretty much if you think about watching movies. So each movie is given a weightage based on the previous watching preference of the viewer. Does that explain? And that's okay?
That's really clear. Thanks.
Okay, right. So let's look into what we were doing here. So now it's pretty much same we did only for list. Now we're going to do exactly this. Now when we for the list, we're going to do for all the 4 restaurants, all the 5 restaurants, and that's what we did. So for list, we calculated took all these attributes, multiply with all of them, we got 40. Took all these attributes, multiplied by the second restaurant, got 32, then so and so forth, all the list for the list. And then we took Adam, and we took again the 4 attributes to Adam. Now these values are different. We multiply again by all the 4 attributes and sum them up. The value is 48. Then again took these attributes for Adam and then multiplied with the attributes of the restaurant. We got 42 and so forth for that one. And same thing we did for Jill. So for Jill also we have like these 4 attributes. We take these 4 attributes for Jill and multiply by the 4 attributes for corresponding restaurants. And then we get a single value for each one of them. Now, based on this, it's very easy for us to make a recommendation or possibly see which restaurants they will go or would not go. So for example, for Liz, the best is the first choice we can make, or basically the best recommendation we can make is Dog Lane Cafe, and possibly followed by Chili's, and it's unlikely that she's going to go for McDonald's and Burger King. Similarly, for Adam, we can say his preferentially the first choice is Dog Lane Cafe, followed by Chili's, and if you look at Jill's, she has pretty much the same score for Chili's and Dog Lane Cafe. So based on these, we can make, so this is what essentially happens in a matrix multiplication, okay, or a dot product of two matrices. And that's why when we did previously a dot product over here, the values look very different because that was a dot product. So you're taking all the column values, multiply by each individual row values, sum them up, and that's why this value becomes 55 over here. Okay. So this is very simple about matrix multiplication. We see an example of how to use them in a bioinformatics scenario. So before going into that one, I just want to talk about conversion of a matrix into a data frame or a data frame into a matrix. This is really crucial because sometimes the data which you are having or you might have brought into R, imported in R, could be in the form of a data frame. But the downstream application or the downstream package you are going to use for analysis may expect the data into account, maybe expect the data into a matrix format. So for example, DEC2, which is a very commonly used package for differential expression of features across different sample or groups. So features could be gene expression. So you might be looking gene expressions between controls and treatment. So when you're trying to feed the data in, its expected format is that the data should come into the form of a matrix, not in the form of a data frame. So let's say we're first going to create a data frame. So count data, we are using the function data.frame, and then we're providing what are the genes are, what each sample values are, and we end up getting a data frame out of it. So this is the data frame. If we simply say class count data, it is going to tell us that it is a data frame, right? But essentially what DEC2 needs it, if let's say we want to put this into DEC2, that's our next step is, so we have to convert it into a matrix. Now, one of the key things about matrix is that we can't have characters and numbers in the same, characters and numbers cannot be part of the same matrix. The data has to be of the same type. So essentially, if you want, we have to provide only the counts, which is the integer values here, and we somehow need to get rid of this character column over here. So what essentially we can do is we can, using the gene names rather than having as a column, we can use them as a row name. So first thing is we assign the gene column as row names. Once the gene names are available as row names, we get rid of the gene columns. Then we will be left out with only these number values as a part of the matrix. Okay, so let's have a look at that. So this is the first step is trying to assign the gene column as the row name. So what we did is row names, count data. So essentially, the row names of count data are assigned by count data $G. So basically, this column values are used as a row name. So that's what this now, instead of having 1 to 5, we have distinct row names now. Now, the next step would be to get rid of column number 1. So the easiest way to do is subsetting is to use -1, which is dropping the column 1. So that's what we're doing at line number 231. We are dropping that particular column. Now, if you look at, so now it's fine. It's just, but it's still, it's a data frame. So if you check class count data, it's still going to say that it's a data frame. Though these values are all numeric, we don't have any characters and all, it's still a data frame. So we have to explicitly say that, okay, now convert it into a matrix. And for that one, we use a function called as.matrix. So that's what we're going to do in the code in the 238 line is going to do. So we are going to say as.matrix and count data. So this count data, we're going to convert into form of a matrix and assign that to a variable count data m. So let's run that code. And if you say count data m, there's no visual, visually, there is no change between count data and count data m, but let's look at the class of count data m. It says it's a matrix. Now what we are having is as a matrix. This can be now fed into DSeq2, and DSeq2 will take it and will start processing downstream analysis. Occasionally, it may be possible that you got a matrix output from some function or some analysis, and the next step you want to convert it is into a data frame. Sometimes that may be a requirement. You can do that way as well. So the function for that one is as.data.frame. So we provide the matrix, and outside we say as.data.frame. So essentially, the matrix is now going to get converted into a data frame, and then will be stored into a variable called count data d. So let's have a look at that. And count data d, again, there's no visual visibly change, but let's have a look at the class of those ones. So right now, count data m is a matrix, and count data d, which we just created, let's see, that's a data frame. So essentially, what we did is we converted a matrix into a data frame, and from a data frame, we could convert back into a matrix. So this possibly is some of the operations you may end up seeing it. Any questions here with respect to it? So all the subsetting and all, we talked about it when we looked at the data frames. Okay, the next thing is I'm just going, this may sound a little bit, maybe it's a little bit complex, so but stay with me. Hopefully I will be able to explain what I'm trying to convey is how the dot product can be used for normalization of data. So let's have a look at our count data d table. So I'm going to just print it over here. So this is a count data d. D is essentially a it's right now is a data frame, but there is an essential, it's a very good function in R which calls summary. So if I have any kind of data table here, is like these are numeric, but even if you have like factor data or anything else, you can get a summary of your data table, and the function is summary. What it provides is it gives you an overview of what kind of values are you having in your data frame. So for example, here it gives that for sample 1, the minimum value is 12, maximum value is 452, the median is 222, and mean is 223.6. Same, it provides the same information for all the 3 samples. So before going into deep into analysis, if you want to have a quick, you can say a view of what the range of your data is, how the values are distributed, possibly summary is a good function to give you an insight into your data. All right. So here, what I'm going to use downstream is count data m, which is the same thing. So let's say this is the matrix. And we have 3 samples, and these are the expression values of all those 3 samples. I think you can run summary even in the matrix as well. Let me try. I'm sure it should run, but yeah, so it works on the matrix as well. So it provides for the matrix that for sample 1, these are the values, sample 1, sample 2, and sample 3. So let's say these are the 3 samples. We have done RNA-seq on it, or basically ChIP-seq or whatever it is. And these are the different features. We have measured the values corresponding to that, some expression or enrichment, whatever these values could indicate, depending upon the kind of analysis we are doing. But what we realize immediately is that the mean values between all the three data sets is very different. The sample 3 has 157, whereas sample 1 has 223.6. This is a small number of genes, but essentially if it's, let's say it has 20,000 genes we are looking, and if this is the kind of mean we end up seeing, then it raises suspicion that we can't have like all our genes to be expressed almost like 1.5 times the sample 3. One of the reasons why we are seeing this such a high value is maybe we end up sequencing sample 1 to much higher read depth. So we sequence, let's say we end up sequencing this one for 20 million reads, and here we only did 15 million reads. So that's why the difference is we're seeing this mean higher in this case. So to come around that, there is something you can say, there's not, in order to do the normalization, we can calculate what we call as the scaling factor. So and in most of the times when you're trying to normalize the data, the data are always scaled down to the lower value. The reason behind that is because if you are scaling up the data, let's say if you increase the value of 157 from 223.6, then if there are any artifacts in the data, that artifacts gets multiplied as well. So you are actually, what you can say, inflating those artifacts. So what rather than what we want to do is we want to squeeze if there are any artifacts in any of the samples. So when we break down the sample 1 values, is somehow we are actually squeezing that artifacts rather than inflating that one, so that we have a good statistical, the values that comes out are more statistically significant, or they hold the statistical significance when we verify with other methods, and so on and so forth. So let's say this is our normalizing vector. So normalizing vector is nothing but the mean of all the three samples, so 223, 189, and 174. These are the values. Then what I'm doing in the next one is trying to calculate something called the or normalizing values or scaling factors. So if you look at the normalizing values, since we are scaling down, we don't have to scale down our sample number 3. So we are just keeping that as 1. So we keep those sample values as such, but the values of the second column, we want to scale down by a value of 0.8. And of sample 1, we want to scale down by a value of 0.7. Okay, this is what we want to achieve. So we want to scale down these values, all these values by 0.7, and all these values by 0.8, but want to retain the sample 3 because that's our lowest read depth sample is. Okay. Now, in order to do that, we're going to do a sort of like a dot product. But before doing that, we're going to create something called normalizing a matrix. So just bear with me. I'm just going to clear it for a minute and Control L. Okay, and let me. So these are our norm values, and from this one, I'm going to create a normalizing matrix. And let's look at how the matrix looks like. So in the matrix, what happened? What we have done is all these values are now represented across the diagonal. So basically, the first, with respect to the sample 1, we have put the value 0.7, and that's the scaling factor of only sample 1. And scaling factor of in here we put 0, 0, and this is 0. And for the second sample in the second row, we put the sample basically scaling factor. And for the third sample, we put in the third row. And why we did that, why we have done that. So let's, I'm going to show, basically just put the, let me put the count matrix first, and then we will see what essentially it happens as. Okay. And okay. So what we are doing is we take the, so we are multiplying this matrix, count data matrix, with the normalizing vector. So what we are doing essentially is we're picking up the first row the way we have done for a list. So similarly, we pick up the gene 1 and multiply by the first column, right? That's what we did in case of a list. We take the list preferences multiplied by the attributes of a given restaurant, like Chili's, which was in columns. It basically was in different vectors. What I'm saying. So the list preference was across each in a single row in each column, whereas the restaurant attributes were each restaurant's attribute was a single column. So what we do here is we take these 3 genes and multiply by all these 3 values. So because this second and third value at 0, these gets multiplied by 0. So essentially they basically sort of taken out of equation. The only thing we are multiplying is number 12 with 0.7. So the number 12 gets scaled down by 0.7. Similarly, when we do for the second gene, we're essentially going to do with this same multiplication. And so forth. As we keep on doing this one, so for the second gene, we're going to again multiply by the first column and the second column and the third column. Okay, so let me go one by one. So for example, 80K1, this one we picked up, multiplied by the first column, which is our sample 1. So this becomes 0, this becomes 0 because we are multiplying by this value and this value. So the only this value has multiplied by 0.7. So this we get 8.47, whatever the value was. So it's scaled down by that value. Now what we do is take the same 80K1 3 values, multiply by the column, second column, which is, think about the second restaurant, and we have 0.0. So the first value gets ruled out, third value gets ruled out, only the second value gets multiplied by 0.83. So the second value gets scaled by the value we are looking, 0.83. Now we go again, take the 3 values, multiply by the third column. So the first 2 values are 0, so they get ruled out. The only thing that multiply 23 times 1, and that's the value only retains. Then we take for the second gene, all the 3 attributes, multiply by all the 3 columns, and we get the values here. So this way, what we are taking every time when we are doing this, because of the dot product, we get the values like only one particular column, like each column gets scaled by their corresponding scaling factor. Now, the question is like, wasn't there an easy way of doing it? Yes, it's an easy way. If you look at this, a small matrix like 3 samples versus 5 genes. But if we're trying to think about something at the scale of 23,000 genes or 53,000 genes, it becomes a really huge data set to do any normal multiplication. So in that case, this matrix multiplication is really, really very fast. And that's where we want to take advantage of this dot product of 2 matrices. Now, if you look at the summary data post all those things, we'll see that now the mean is pretty much the same. So we have somehow scaled down all those 3 data sets. Now we can compare the gene across the 3 samples. So that's, you can see a sort of an application of dot product in scaling up the data or scaling down the data. Or scaling of the data, let's say, is simply the scaling of data by use of dot product. Any questions here? But this is one of the cool applications you will see, and that's why linear algebra is so strongly used in data analysis, whether if you're doing the data science kind of like regular data analysis or even in bioinformatics also. Matrices are really play a crucial role, but most of the times, let's say if I'm doing analysis, I don't see that happening. People have already wrote the functions to achieve the matrix multiplication, scaling, and everything. So all these things are happening behind the screen. I'm not saying it. What I see is I put the matrix in, I get the scaling factors, and then the data gets scaled, and I only see is the final scaled matrix. But this is essentially what is happening behind the scenes. That's what I'm just trying to, and if this is what is happening over there. Okay. So the next object type is called arrays. Arrays are, you can say, so matrices are 2-dimensional objects. So you can think about have a number of rows and number of columns. Arrays are basically multi-dimensional objects. So one of the easy way to understand a matrix is, let's say, we are doing time series kind of a data analysis. We have time series data sets. So we can have for time 0, we can have our data. Okay. So we have certain number of columns, then we have certain number of rows. Each rows will represent genes or any features we are interested in. Now this is time 0, let's say time 15. So time 15 will have the same samples and have the same genes. The only thing is the time had changed. So that basically essentially becomes a next dimensional objects. And this is equal to t equals to 1. Then we can also have another time series. So we can say t equals to 2. So essentially what we are doing is we are actually moving into the 3rd dimension with respect to our data. So we have X and Y dimensions for regular data storage, like attributes versus samples. And in the Z direction, we can have an additional dimension added to it. And that's what arrays are. So array can have a three-dimensional object stored into it. And the dimensions of array are generally represented x, comma, y, comma, z. X is the row, y is the column, and z is the, you can say, stack or the depth. So for this one, for this particular one, z is equals to 1. This is z equals to 2. This is z equals to 3. Right? So that's how the depth is. And x and y, x is basically the number of rows or attributes we are looking into. Y is the number of samples or columns. That's why that's the x and y and the z. So an array has like a three attributes associated with it. So here what I'm doing here is in creating an array which is three-dimensional. So the values I have is 1 to 24. The dimensions are, I want to have 2 rows, 3 columns, and 4, you can say, stacks. The data has to be in 4 stacks. So let's have a look at that one. And if you look at, so this is the frontmost array. When you say comma, comma 1, this is the on the topmost array. Or if you look slice-wise, this is the top slice, and it has 2 rows and 3 columns. This is the second slice. This is the third slice and fourth slice. So from the depth is the 4th data frame we are looking at. These are, if you want to get the first row of all the arrays, we can run this code. And it represents, so this is the first row of array 1. This is the first row of array 2. First row of array 3 and first row of array 4. And those are the values which are basically pretty much represented. This is the first, sorry, the vertical, you have to look at the vertical ones. So the Z direction is this one. This is the basically each data frame. The same is here, you're trying to get second row, third column, second row, third column of all the data frames. So second row. It's basically second row, and the third column value is 6, 12, 18, 24. So 6, 12, 18, and 24. This way we are picking up a very specific value, second row, third column of the second slice. So this is second slice, second row, and the third column, so the value would be 12. Yeah. But this is, again, you're not going to use a lot, but just for the sake of information, I'm just covering that particular let's say material. So I think this pretty much covers with respect to the data types that we have in R. So we talked about data frames, lists, and then we looked into matrices and arrays. So if I recommend which one you should really have developed your expertise in, then I would recommend the data frame is the one you should have really clear-cut idea about subsetting and playing with the data set. So need to develop a really thorough understanding of a data frame, and that possibly will take you through 90% of your analysis. You don't have to worry about any other kind of data sets. Any questions here? I'm just going to look into what files I have, because the next part we are going to discuss about is, in a way, importing data in R. So that's exciting, because now we know a little bit about data frames and everything. Now we want to bring our own data, which might be available to us in R, to start analyzing, at least start looking at it, what columns has, and can run summary function on it to give you some idea about what are the attributes associated with it, what each column has range with respect to the different data types you have. So when you're trying to import a data, there are different functions out there. And you can use multiple functions to achieve exactly the same thing. Okay. And these are some of very common data frames I have listed, data frames, very common functions I have listed to import data of certain type. And I assume these are the most common you will encounter. One is called read.table. So you can import a table. So the first thing you provide is the file name. Then you specify whether your importing data has a header or not. If it has a header, you're going to say true. By default, the value is false. So by default, it is going to think that there is no header. So if there is a header, it's going to convert that header into one of the rows. So if it is a header, you should say header equals to true. Then we are going to specify what they're going to be the separator, how the values are separated in our data set. or in our table. So that in case of comma separated values in CSV files, our values are generally separated by comma. So we have to specify separator is a comma. If we are working in a TSV file, which is tabbed separated values, then we have to say, okay, the values are separated by tab. So based on whatever separator we provide is going to separate the values in each row. The values in each row will get separated based on the separation character we are going to supply. Then there are some additional parameters. One of this one is quite common, string as factors. So by default, most like read.csv or read.table, what they do is, if any of the column has character data, they try to convert them into factors by default. So if you have a factor data in column, that's great. Okay, it get converted into factor, but sometimes not every column has a factor data. So in that case, it becomes a problematic or maybe nuisance. So then what you can say is string as factor equal to false. So you stop being converted into factors. The other function is read.csv. Again, you provide the file name. You say, if you have a header, you say true. And then by default in read.csv, the separator is a comma by default value, but you can always override it. You can provide a different separator. So let's say if your data has a separator as semicolon, you can simply say separator equals to semicolon. Then the default value gets overwritten by semicolon, and now the program or the function starts separating values based on semicolon rather than colon. But to separate for semicolon, there is another function, read.csv2. So that is default is semicolon, but you can interchange these ones. The only thing you have to remember is to specify what is the delimiter in your data set is. This is read.delim. These are two different functions here that essentially the data is actually separated by tab. So that's how you specify the data is separated by tab /t. So I'm going to import a CSV file, and we'll show you that 3 different ways and how you can use. These are designed to import different data types, entirely different, but you can manipulate, or you can just say customize these functions to import a file of your choice. So I have a read.csv. So what I'm going to do is I'm going to import this female mice weight.csv. So if I say, so I have done list.files that list out what are the files I have in this particular directory. So let me first use the read.table function. So I'm going to say d1. So when I read the table, I want to assign to a variable. I'm saying d1 is the variable. I would say read.table. And inside that one, it's a CSV file. So I'm going to say female mice. And since it's a CSV file, the only thing I'm going to specify is a separator, and separator is comma. And I know that this file has a header. So I'm going to say header equals to true, because by default it is false. Okay. And now if I say head D1, I'm looking at the first 6 columns, rows of D1. And this is the data is imported in here. So that if I specify the separator is comma, I can use read.csv. Let's do that. Maybe let's do it D2. Read.csv. And I'm going to say, this is the table CSV file I want to read in. And by default, header is true. So I don't have to specify that header is true. And the separator is comma. That's what I have my data. So I don't have to specify anything else. And now if I look at head D2, we get exactly the same thing over here. Now let's try read.csv. Okay, let's do D3. Read.csv2, and I'm going to say female weight. Now in read.csv2, by default, the separator is a semicolon. So if I use that one, there is no semicolon in my data. So it's not going to separate the values rather than it will, because there is no semicolon, it's not going to separate them and present them everything stitched together as a single value. So here I have to specify, okay, the separator is actually a comma. And yeah, it pretty much imports it. Let's try the read.delim. This is the last one, D4, and read.delim, and we're going to say female mice. That's what I'm importing. Again, I'm just simply going to do the separator equals to. Here it is tab by default. I'm going to change that it's a comma. And so though these functions are designed to import data separated by different values, by different, you can say, as delimiters, we can change them, we can customize them based on our needs. So let's say for some reason my data is not separated by comma. It so happens that the data is actually separated by underscores. I can simply say separator is equal to underscore, and the values will get separated by, so wherever it sees an underscore is going to separate those values into different rows, basically different columns. So that's how it works essentially. Any questions with respect to data import using these functions? Okay, that's cool. Now I'm going to just show you a quick example. So sometimes you may have to extract out data from SQL database, relational databases, and very common of those is MySQL. And I'm just trying to, just in case if some of you would like to access data from a SQL database, how to go about it. So that's the next section I'm discussing over here. So let me clear the screen first. So the package you will need to access an SQL database is rMySQL. So we're trying to load that package. So no, sorry, I don't want to load this package. Control escape. Okay, I already have that particular package installed, so I don't want to do that. I don't know why I always have it commented out. So I'm going to load that particular package. Okay, I loaded the package. The first thing what you need to do is to establish a connection with the given database. Whatever the database you are going to using, you have to connect to that particular database. You provide that the database is of MySQL type, and then you're going to say what the username is, what's the password is, what the database name is, and what the host is, actually what's the location address of that particular database. Once you provide all these parameters, it will create a connection, and that connection is stored into my connection. Then you can, since the connection is there, now you can use different functions like DB list tables. It will tell you what are the different tables are there in that database. So sometimes database have like thousands, hundreds of tables. Each table have very different kind of values stored inside that. You can also look into what in a given table, let's say what of the table we are looking into, what are the different columns in that particular table is. We can say DB list fields is going to give you the different columns that in that particular table. And then we can basically fetch a particular table based on a query. So this is a SQL query language. I'm not going to go in details of how SQL query language is written. But if you're trying to use an SQL, you have to just read or basically learn how to query an SQL database. That query is going to go here. And based on this query, it is going to go to a particular data table and pick up the variables that satisfy your criteria and fetch all, basically going to get all those values and store them in records. Finally, what we can do is we can fetch these records and can store them into a variable. So that's the SQL works. Now I'm going to give an example of using this SQL. And for this particular case, we are going to connect to UCSC database, genome database, which is MySQL. So let me comment. I'm not going to install it. So we have already loaded the MySQL package. I'm going to establish a connection, MM10. And here I'm looking at the mouse data set in UCSC database. So I'm naming the connection as MM10 connect. Can name any name, whatever, because it's a variable. You can specify any name whatsoever. But on this side, this has to be very specific. So we are saying DB connect. So connect to the database. It's in MySQL formatted format database. User is genome. So the genome user doesn't have a password associated with it. So it will let you access it. The database name is MM10, and this is the site or basically the address where the database is hosted. Okay. Now what we're going to do is, so this connection is established. What we're going to do is use DB list tables function to get, okay, what are the different tables that are available at this particular database. So let me establish the connection first, because that's been done. Let me get all the tables. So if I say dim tables, or basically length tables, it's a vector, so let's say length vectors. And it's going to tell that in MM10 Connect, which is MM10 database, there are 785 different tables in that. So now you can simply say tables and then pick up. These are the 785 different tables that are there in that UCSC database in the RefSeq. So depending upon what you're looking for, which table you're interested into, you can pick up that particular table. So let's say I am here, I am looking for RefSeq genes or the ref gene. So I'm going to look for that particular table. So let's look at a table which is ref gene somewhere here. It should be. Yeah, this is the table 583. That's the table I'm going to access because that's what these are reference genes. I'm trying to look for those ones. So I'm going to use that particular table. So now what I'm doing is, so before getting what I want from that particular table, I would like to see, okay, what are the different columns in that ref gene table is. So I'm going to use db list fields function, and I will say db list fields using MM10 connection in the ref gene table, provide me what are the different fields are. And it tell you that these are the different fields that you have in that particular data set. So you have bins, names, chromosomes, strand, the gene is located on transcription start site, transcription end site, CDS start site, CDS end site, exon counts, exon start, exon ends, certain score associated with them, and all that values are there. Now in this one, let's say I'm interested only in chromosome 1. So I want to pull out from this big table only the, you can say, entries that are corresponding to chromosome 1. So then I'm setting up a DB send query using the connection. I'm writing an SQL query over here. And the query, what I'm specifying is in the Chrome column, pick up only the one satisfying CHR1, which is a chromosome 1. And once I do that, connection is established. Okay, forget about the warning messages. And now from the records, I'm going to fetch the records into data column in a data variable. Now, if I look at data, let me do head of data, otherwise it's a very big table. And you will see all these things. Now we fetch the data from a like UCSC server, and you can see these are only chromosome 1s, and these are strand information, transcription start site, and all different variables that this we're able to get it and store into data variable. And you can use it for downstream analysis, whatever you would like to do it. But at the end of it, once you have done the fetching, it's a good idea to close the connection. And you can say, basically DB disconnect is going to close the connection for that site. But this way, now the data is already stored into a data variable, which we can use. Any questions here? Okay, so the next part is, if you have data coming in from any other kind of source, like other statistical packages like SPSS, DTA, Octave, there are functions meant for each one of them to import data in R. Even from Excel, if you have an Excel sheet, a table, and you have multiple sheets, there is a function to achieve that. I think I forgot to get this session, but next session I will definitely talk about importing data from Excel, and will give you what is the function is. But this is the link where you can visit, and it provides a really more extensive functions that can be used to import different kind of data types. Finally, towards the end, what I want to talk about is storing data, like either or basically saving the data. And this time, this saving of data is more from the perspective that you're trying to share the data you have in your R session with another user, so he can take exactly what you are doing, have the same variables, have the similar kind of data sets, and he can import that data into, you can share through you send him whichever format, through email, attachment, whichever way. Once he or she has it, they can import it into RStudio and have exactly the same variables you are working with. So how that can be done. So I'm going to talk about some of those ones. Okay. So first I'm going to create a data frame called chip2. So this is a chip2 data frame. Chip2, so it's a data frame. The chip2 data frame, if I want to save just the data frame, just one data object, could be data frame, could be a matrix, could be anything else. What I can save it is and save into a format called .rds. So I can say save, provide the object name. So that's the name. Object name is the name of the matrix made of the data frame that I'm going to provide there. And I'm going to say, okay, what was the file name once it saves it? So I'm going to say save chip2, file name is enrichment.rds. So essentially what you can save it as a, you can say Excel, you can CSV file or TSV file and share as well. The advantage of saving it in our .rds is it's a binary formatted. So your file with CSV could be like, let's say 500 megabytes. In RDS format, that could be like 10 MB. It's small, really small. So it compresses it to a greater extent. So those formats are really useful. So I'm going to say list.files. So some of those files already exist, but you can say that enrichment.rds this is what we just now created. So this time we saved only one particular object type, but sometimes if you want to save multiple ones, there is a way around that. So let's say we have chip2 and we have some vector called selected positions. Then we have a sample name, which is a variable, and we have a read depth. But these are the, you can say, 4 different variables we want to share with another user. We want to share the data set also. We want to share these variable information also. Then what we can create an object called, we can save it in the format .rdata. We'll provide the data frame. We provide these variables, selected position, sample name. I didn't mention read depth, but you can also add here read depth as well. Oh no, I started the wrong read depth. Yeah, so you can store all these 4 variables into a single file. And then again, it's a binary compressed, save it to another user collaborator. They can import it into their R session and they can go from there. So they have exactly what you have it. But if you want to share like everything, even environment variables, the packages, basically what you have been loading and what everything you have created, including your history, then the best is to create an image of your session. It's called save.image, and you say file equal to session.rdata. So session could be anything. So let's say if I'm doing methyl-seq analysis, I will say methyl-seq analysis.rdata, maybe provide date also in the name so that I know when it was saved. And this is generally what is R always prompts you. So in RStudio, it doesn't happen, but if you simply open R console and start doing some analysis, if you close basically image of all your history, your variables, everything, and just literally stores it. Yeah, so then if you're sending it to somebody, that person have exactly everything what you have done in your analysis. Sorry, my internet connection is unstable. You're able to hear me because it showed my internet connection was unstable. Were you able to?
I missed like, I don't know if anybody else did. I missed like, I don't know, a few sentences before.
So were you able to, like, up to 394 was fine?
I think so.
Okay, so basically in this format, .rdata here, we are actually saving multiple objects, or you can say multiple elements of analysis. So we chip2 selection position, which is a vector, sample name, which is a variable, read depth. So these are the 4 different, you can say, sort of like objects of R, or you can say analysis, basically objects which you have created, and want to share only these 4 to another user or collaborator. You can save them in a file, whatever the file name. I'm here saying compact, but you can change to whatever, and save it as .rdata. So all these multiple things will be saved, and when you send it to the user, to a collaborator, and he imports this data or load this data, he will have all these 4 variables in his environment, and he can do from downstream. Occasionally, you may like to share like everything what you have done in your history, including your history, the different variables, not only these 4, but all other variables, everything what you have been doing, what are the different packages you have imported in your doing the analysis. All that information, if you want to do, what you can do is you can create an image of your session. So that is like save.image. And then you provide the name, whatever the name says. If I'm doing methyl-seq analysis, I will say methyl-seq.rdata. And it will create a single file, which have all my history as well as all the variables I have created. And once you send it to the user, the next user, the user can import it, will have all the basically variables to him, and also have information on what all packages you have loaded. So that he can recreate your environment and see what, if there's and can carry on the analysis downstream from there. Once you, let's say if these data, the same object somebody sends to you, you want to load it into R, you can use the function load enrichment.rds if you're a single data object. If it's R data, you again use the same function, and then it essentially load all those data inside your R session, and that is available to you. Many of these packages, what we are going to use, essentially like any package you look around will most of the times comes with a default data set. And the idea behind that is they will you can use that data set to play with the functions of package, to learn more about that package, how you can use it. So they will provide you a dummy data set. So similarly, for example, ggplot2 is one of the libraries used for generating graphics in R, very, very popular. And we'll look into the last session about it and learn about how to do graphics in that. Comes with a data set called diamonds. So, and it's a loaded library. So I loaded the library ggplot package. And now I'm going to load diamonds data. And if you look at add diamonds, this is the data set that get loaded. So it has multiple columns, like multiple attributes, you can think about it. And these are the different, I think there are different, each row represents a properties of a different diamond. And this is a little bit different. If you look at it, it has an additional, you can say column, it's an additional row other than the column names. And this row specifies what kind of values are there in each column. So this is double value, which is integers. This is ordinal data. So that the diamond quality is like good, ideal, good, premium. So there is an order associated with it. So it's an ordinal categorical data. Color is again ordinal. So maybe some preference with respect to people like certain color, not the other color. Clarity, again, it's an ordinal data. Maybe more clear diamonds are more preferred. I don't know. I never bought a diamond, so I have no idea. But yeah, so depth is an integer. The depth is again a decimal, so it's a double. Then you have table price. It's basically table is assigned as a double, but doesn't. Maybe that's why they would like to have some integer value, basically some decimal values for that one. Price is looks like is in an integer format. I'm not sure what this price indicates, what's the value is in, but then the rest of the parameters, like maybe these are the dimensions of the diamond, and these are in X, Y, and Z. So this is a little bit a different format of data frame or importing a table. Sometimes you see it, but yeah, that's this row is nothing but just specifying what is the format of data is in each column. So each package, if you load, I won't say each, but most of the packages come with a default data set, or no default, I would say dummy data set, which you can use to learn more about how to use a particular package. I think this is what I want to cover today. Just short 5 minutes over the top. Sorry about that. If you have